Okay, here's our final example here in the lecture for related rates. Water is being pumped into a trough at 2 feet cubed per minute. So I tried to recreate this drawing here as best I could on paper. So you see this trough, and the cross section, if you will, in the front is a triangle. And then the trough just goes back, horizontally. So in the front, you can see all the labeling. The distance across the top is shown down here. That's 3 feet. The height of the whole thing is 5 feet. This depth of the trough is 12 feet, and that's all the way around. And then you've got some water in it already, and we're just labeling the height of the water as h feet. And then you see my drawing of this like pipe that's coming in, and more water is trickling down, and that depicts the 2 feet cubed per minute of more water that's being pumped in. So if you want to take a moment and try and recreate that drawing, things like this, if they were given to you on a quiz or a test, I would have an image there of that picture, so it wouldn't be. I think I did all right drawing it, but it'd be this nice crisp, picture. Okay. Part A. What's the question? How fast is the water level rising when the depth is 1 foot? Okay, so obviously water's coming in, so the volume of water is increasing, but then the water level is obviously rising. And if you think about it, because of the shape of the trough, right, the water level, it's not always rising at the same speed. At first, because it's so narrow, the water level is rising very quickly. But as it gets closer to the top, the water level doesn't rise nearly as fast, even though the same amount of water is still coming in because it's wider, right? Okay, you get the idea. So how fast is the water level rising when the depth is 1 foot? Okay, now this question is just on another level of difficulty. And so that's why we're doing it here. You're going to see questions similar to this in homework. And so have this example in mind and kind of go through the same theme. Some of the things that we do in this example, the way we go about it, just getting the equation. That's going to be like 90% of this problem is just, can we get the equation? As we're working through it, you might think to yourself, I never would have thought to do that. That's okay. That's why we're doing it together. Recreate that same approach when you see questions that have a similarity to this one in your homework or wherever. Okay, here's what we need to do. We need to identify what the changing quantities are. And there's two. There's two quantities that are changing. Okay, what are the changing quantities? That's not even like jumping off the page here, and sometimes students miss it. Or when I ask that question in the classroom, it takes a moment. What are the changing quantities? Okay, so one is the volume, right? Water is being pumped in, so the volume of water is changing, okay? And the second one is the depth of the water, right? Or maybe we call it the height of the water if we call it h. So the depth of water is changing and the volume are changing. So let me just show you. We kind of try to scroll up a little bit. The volume of the water, we're going to call that V. And the depth, or maybe you call it the height of the water, and since it was in our drawing as h, we're just gonna call that h. Now the volume of water is always changing at the same speed, right? 2 feet cubed per minute. But the height of the water changes at different speeds, right? When the water level's low, it goes fast. When the water level's high, the height changes slower. Okay. Let's take a look over here. We want an equation relating V and H. It's the same thing that we were doing earlier, like get an equation with X and Y, right? Get an equation with theta and y, or theta and x. Just now it's going to be a lot more difficult to get there. How do we get an equation relating the volume of the water to the height of the water? Okay, wow. So first thing that we want to notice is just the shape of the trough. So the volume of the water, how do we get the volume of the water there? So if you think for a minute, wouldn't the volume at any one moment, and also keep in mind it's only the volume of the water. I mean, the trough itself has a volume, but that's not what we care about. The volume of the water. At any moment, wouldn't you take the area of that triangle and multiply it by 12? Right, that 12 is constant. Right, it's always 12 feet, deep, if you will. But this little thing is what changes. So as this gets bigger, well, we still are going to multiply by 12. So we want the area of this little triangle times 12. Okay, that's a great place to start. At this point, we're now going to say, okay, let's put all of our focus on getting that area at any given moment, or for any given height. So here's what we're going to do. There's a lot of like little steps leading up to it, okay? So I'm just going to draw that cross section of the front of the trough. And I'm going to relabel, the parts that we have. So we know it's 3 feet across the top. I know it's 5 total feet tall for the entire trough. Of course, we're only concerned with the area of the water. So I'm going to draw the water, and I could draw this anywhere, but let's just draw it about there. Here's the water, and then we know that that is H. Okay. Now there's another piece to this whole picture that we need to label, and that is the distance right there. If I want to know the area of the water, well, I've got a triangle, and we know, because we're right, we know all of math, is a potential here. The area for that little triangle is 1/2 base times height. So the area of the water that I'm looking for, 1/2 base times height. Okay. So we're off to a good start. We got H involved. But now we've got this other unknown, the base of that triangle. But now this is where you might, you're starting to think, wow, I would never think to do that. And that's okay. There's no problem with that. That's why we're doing this. We need to get the base in terms of H. If we can get B in terms of H, then we can substitute that right here, and we can get the area in terms of only H. And then we're just a step away from getting the volume, right? Multiplying by that 12. Okay, how can we get the base, this distance, in terms of H right here? And the key is these other two numbers. Okay, we're going to use all 4 of those together, and we're going to make this happen. Now again, think of all of math, all the geometry that you've ever learned could come into play at any moment. Can you think of a way to connect B and H in an equation that would also use the 3 and the 5? Now, typically when I teach this live, it'll take some time before somebody makes the suggestion to how to connect those two. Right? Obviously, we're dealing with triangles here, but it's not going to be Pythagorean theorem. It's not going to be any trig. We're not working with an angle. At least that's not the most straightforward way to do this. It's just good old geometry, and maybe geometry you learned quite a while back. The concept we want to take advantage here is similar triangles. Isn't the triangle for this water a similar triangle to the entire trough? Yeah. And in similar triangles, the corresponding sides are in proportion. So here's what we're going to do. You might say, okay, I'll just show you all my work right here and talk through it. We can say, to set up the proportions right, b over 3 is the same as h over 5. Those are in proportion. That distance to this is the same as this to that. And if we can say b over 3 equals h over 5, we can then multiply the 3 over here, and maybe we just say b equals 3/5 h. Now we have the base in terms of the height, and we can put that 3/5 h in for the b, 1/2 base times height, clean it up. We've got 3 over 10 h squared. The area of that water is 3/10 times the height squared. Okay, so when you see problems like this in the homework, right, there'll be some trough questions, but there might be some other, similar things. Take advantage of similar triangles, or maybe it's not even similar triangles, but it's like the same thinking, the same kind of thinking where you're setting up that cross section, that sort of thing. Okay. Once we have the area in terms of the height, our goal is to get the volume in terms of the height. Well, we're really close. As we discussed a moment ago, the volume of water is 12 times the area, right? Because that trough is always 12 feet deep. So if we just multiply that area by 12, we'll have the volume in terms of the height. So V equals 12 times 3/10 h squared. And we'll simplify that. Let's see, if we multiply by 12, that'd be 36 over 10. 36 over 10 you could reduce to 18 over 5. V equals 18 over 5 h squared. We got the volume in terms of height. That's awesome. Okay, we got the equation relating the quantities. Wow. It only took 12 minutes. Okay, where to go from here? Once we have the equation relating the quantities, now we take the derivative with respect to t for time. Okay, no big deal here, right? The derivative of v is simply dv over dt. This, well, multiply the 2 down, 36 over 5h. And be sure to put the dh over dt on the end. Once you have your related rates equation, now we know how fast the volume of water is changing in terms of how fast the height is changing. Okay, now which which derivative are they asking about? Of course, it's the dh over dt, because that describes how fast the water level is rising. So this is the number we want in the end. So that must mean that they told us how fast the volume is changing and the height at whatever moment they're asking about. Well, yes, they did. So we're in good shape here. Let's just pull this on up. We know that the volume of water is changing at 2 feet cubed per minute. And we want to know how fast the water level is rising when the depth of water or the height of water is 1 foot. So that's equal to 1. So boom, plug in 2, plug in 1. And we got this. Let's see, if we multiply the 5, divide by the 36, and reduce, dh over dt will equal 5 over 18. You could answer as a decimal there if you prefer. No big deal, but I'll just keep it as the fraction. 5 over 18, it's said to include units. I believe it did. So you might say, okay, 5 over 18, and to get the units, I mean, maybe just instinctively, you know it's feet per minute. But if you're kind of thinking, okay, how would we get it? So take the units of the height divided by the units of time. Height is in feet, time is in minutes, because they said the volume was in minutes, right? So 5/18 feet per minute. And that seems to make sense. What's that, about 1/4 of a foot per minute? That's a pretty big trough. It's going to take a while to fill that thing. Okay. That was part A. There is a part B, but kind of like the last problem, we've done the vast majority of the work already. Part B here says, if the water level is rising, oh, we're changing things up. The water level is rising at 3/8 feet per minute when the depth is 2 feet. How fast is water being pumped into the trough? Okay, so imagine the same trough, but new scenario. We know how fast the water level is rising when the depth is 2 feet. Can we go back and figure out how fast water is being pumped in? That's pretty interesting. Okay, well, if it's the same trough and it's, we're still volume and height or depth, then we know we still have this related rates equation. So we don't have to bother, obviously we don't have to bother finding the equation relating volume and height again. We don't even have to bother redoing the derivatives with respect to t. We know it's based on dv/dt equals 36/5h dh/dt. We're just going to change what we know and what we're looking for. So here we're looking for dv/dt, and they tell us the height and they tell us how fast the water level is rising. So we'll just plug those right in, and we can almost immediately answer this. Well, 36/5 times 2 times 3/8, and we get dv/dt. In this case, when you do all those fractions, 27/5. You could answer there as a decimal too. Either way is okay. Kind of the general rule of decimals versus fractions. If it's a terminating decimal, then no problem. You can put that in. But if it's a decimal that you would have to round, then stick with the fraction because we want the precise answer. You could also say in this case, since they gave us a fraction here, it's only polite to answer with a fraction. It's like a mathematical etiquette. If they give fractions, then answer with fractions. That's not a big deal to me. Just make sure you don't round something where you could have just used the fraction to get it exactly. Okay, anyway, 27/5. What are the units? Well, volume is feet cubed, time is minutes, so feet cubed per minute, and there you got it. Okay, you guys, that is related rates. Really exciting, our first big application. Go check out the homework. You're going to get stumped on things. It's going to take time. So I'll bring those questions to the Zoom hour. I'll see some of you guys then. Good luck.